start by explaining the problem of presbyopia. This is the problem that I'm going to solve with the technologies I'm going to speak with you about. You can see in this slide, in the upper row, the case of an object which is positioned far away from the eye, and therefore the focus is obtained on the retina. On the other hand, if the object is approaching, the focus is supposed to be obtained behind the retina, and the image should be blurred. In regular cases, the lens of our eye has the property of accommodation, which means it has the property, the ability to change its focal length. And then, by changing its focal length, we are bringing the focus which is obtained behind the retina to the retina. And this is how we can, on one hand, see very well remote objects while we look towards infinity. And on the other hand, we can focus on a book and read the text without a problem. What is the problem then? The problem is that after the age of 45, even if we are emotropes, which means that our vision for remote objects is good, our eye loses its capability of doing optical accommodation, which means that we see very well remote objects, but if we need to focus on near field objects, we will fail to do so. The focal length of our lens will be almost unchanged, and therefore the textbook that we will try to read will be blurred. We won't see the text. So what is the solution? There are several solutions. You know, with spectacles, you have what is called progressive lenses, which are lenses having many focal lengths. And then the user chooses the right line of sight to look through the right focal length to see the object that he tries to see in focus. In contact lenses, you have, and also in intraocular lenses, you have bifocal lenses, which allow you to see well remote objects and near objects, but you do not see well anything which is in between. For instance, you want to watch television, to work in front of a computer, or a woman wants to put a makeup, then they will not be able to see a focused image. So the solutions are only partial. And what we wanted to develop in the last 10, 15 years is to develop a certain optical device that can be a contact lens, intraocular lens, or even spectacles that are monofocals. They have a single focal length. And by adding special scratches, special patterns which are embedded on the surface of those lenses, we perform a significant extension of the depth of focus which is obtained for that given lens. And if we have an extension of the depth of focus, you can look on the second row of my slide. Instead of having a single focal spot, we have now like a channel of focus. And then if everything is properly designed, then remote objects are in focus because the retina falls on one side of the focal channel, and near objects are also in focus because the other end of the focal channel falls on the retina, and everything in between the far field and the near field is also in focus. So this is an all optical extended depth of focus technology that gives you everything in focus from near to far over the full field of view. And in this case, you don't need the optical accommodation capability of the lens of your eye because everything will be in focus. If you use it for spectacles, then you gain due to the fact that you see everything in focus over the full field of view, you don't need to find the right line of sight to have the object you look at to be in focus. And if you use contact lenses or intraocular lenses, then you have everything in focus from near to far distance, and not only the near or the far distance, but also all the objects that are in between. But what is also very interesting with this extended depth of focus technology is that it can solve not only presbyopia, but also what is called astigmatism. Astigmatism is when you have different focal length for the two axes of the optical lens. And since the focal length is different, the image is distorted. But if you have extended depth of focus for each one of the axes, then there is a point, a distance in space that both focal length due to the extension they meet and you have an undistorted image. Now, it is true that for astigmatism, there are other solutions, but this, like for instance, in spectacles, you have cylindric lenses, and in contact lenses, you have toric contact lenses. But the point is that all those solutions, they are good for what is called regular astigmatism. And the extended depth of focus technology will talk with you about gives you a solution which is good not only for regular astigmatism, but also for irregular astigmatism. Now, this is an introduction. Now, how do we obtain this extended depth of focus? So thank you for asking this question. It's a very good question. So until, say, 10 years ago, there were two common technologies to extend the depth of focus of optical lenses. The first technology is called diffractive technology, and the second one is called refractive technology. In diffractive technologies, you generate structures on the surface of your lens. Those are diffractive structures, which means they cause the light that passes through those structures to diffract, to be affected by the diffraction effect. This happens when the structures which are fabricated on the surface have dimensions which are more or less the size of the optical wavelength. The advantage of diffractive optical solutions is that they are flat. They are fabricated indeed only on the surface of the lens, but the disadvantage is that they have aberrations like chromatic aberrations, so the colors are distorted in the image you gain. Also, they have low energetic efficiency, which is also not good, especially if you try to look through those lenses during the night or during low illumination conditions. But as I said, they are flat, they are low cost. So this is the advantage, and therefore they could be suitable for ophthalmic devices. But again, they have low energetic efficiency and high aberrations. The other type of solutions is what is called refractive solutions for extended depth of focus. The problem with refractive solutions is that they are bulky and expensive, so they are less suitable for ophthalmic applications, but their advantage is that they have good optical performance, high energetic efficiency, no chromatic aberrations, but as I said, not suitable for ophthalmic applications. What we have developed is a new type of technologies, a new type of extended depth of focus technologies, which we called interference-based extended depth of focus technology. What we do, we add scratches on the surface of the lens, but our scratches are different than in the case of diffractive optics, because the effect that corrects that extends the depth of focus in our case is not related to optical diffraction, but rather to interference. So we don't have diffraction orders. All the energy flows to the on axis to the zero diffraction order, and therefore we have much less chromatic aberrations, and we have much higher energetic efficiency. Our scratches are larger. They are not in the order of the optical wavelength, but much larger, so there are no significant diffraction effect. What we do have is interference. Now, how do we do interference with lenses? I mean, interferometry is a known field, but they don't use lenses. So the point is that if you look on this slide, you have a lens that makes a focus in this point, in the focal point. The lens is actually an interferometer because the focal spot is the geometric location in which all the rays that pass through the aperture of the lens pass exactly the same optical path. And therefore, this is a constructive interference. And this is how it looks in experiments. The green chart that is seen here is how the focus looks like from the side of the lens. Now we add scratches. The scratches that we add change the interference condition such that the regions which are now painted with black, they become, in those regions, you have disruptive interference instead of constructive interference. And if the black regions have disruptive interference, then you have, instead of a focal spot, you have a focal channel. And this channel has an extended depth of focus. And this is exactly what we want. And experimentally, you can see in the green measurement, you see how the focal channel is indeed much longer, much more elongated in comparison to how the focal spot looked like before. How do we obtain this disruptive interference in the black regions? Well, we add scratches on the top of the surface of the lens such that the rays passing through those scratches have opposite phase. They have a phase of 190 degrees. And when they are combined together with rays that pass through places where there was no scratches, they construct together a disruptive interference. And the result is this extended depth of focus, this focal channel that we get. In this slide, you have a summary of experimental results showing you how you have a small depth of focus in the regular case, regular lens, but when you add the scratches on the surface of the lens and you do it properly to extend the depth of focus, you have this elongated channel of focus. Now, whenever we do this, whenever we extend the depth of focus and generate this disruptive interference, obviously we need to pay with something. And the payment that we do is a payment in the contrast at which the different spatial frequencies are seen with our imaging system through our modified lens. But the point is that we are planning to do this extension of depth of focus for ophthalmic applications. And in ophthalmic applications, the sensor which is behind the eye is our brain. And our brain, unlike cameras, has logarithmic dynamic range. And therefore, if this reduction of contrast that increases eventually the depth of focus, if it is properly designed, if it is matched to the cognitive perception of our brain, and due to the fact that the brain has logarithmic dynamic range, the reduction in the contrast is almost the user of the lenses almost does not feel this reduction of contrast. So it's not only that the image is in focus, but also the resolution and the contrast of the various spatial content of the image is undamaged. Let us look on some experimental results. You have the image above, and the lower image is the focus of the relevant region here. You can see this is without depth of focus. You see that the remote objects are in focus, but the nearby business card is blurred because the depth of focus of the imaging lens is not sufficient. But we take the same lens, add the scratches I spoke with you about, and this is what you see. The remote objects are seen as well, but the nearby business card is now very much in focus, and the letters are visible and readable. Now let us go to ophthalmic lenses and speak about spectacles, intraocular lenses, and contact lenses. This is an example of one of the contact lenses that we have fabricated. Those are the scratches I talked with you about. You can see them. They are fabricated using a regular lathe machine, which is used to fabricate a small quantity of production of contact lenses. Those are experimental results. You can see how this ophthalmic resolution chart looks blurred, but when we add the scratches that extend the depth of focus, the letters become clearer and much more visible. Here you can see several experimental results in which we have embedded this technology into spectacles. So let us look for a second. Let me explain how we do the clinical trials so that it will be clearer for you. So the units, let us look on the upper left chart. So the units are log-mar units. This is the units for visual acuity. Every 0.1 in this scale is one line in the ophthalmic resolution chart. When you now around 0.25 is like 1 diopter of spectacles. Okay, now when you have a value which is close to 0, it means you have good vision, perfect vision. When you have something above 0, it's bad. It means you lose visual acuity. If you have below 0, you have negative number, it means you see even better than regular nominal vision. So let us look on distance object. So in the case of distance object, we took people that participated in our clinical trials, and those people had presbyopia because they were relatively old. They were above the age of 45. We corrected their vision for distance, their distance vision, and you see that for distance, their visual acuity is close to 0, so they see well. But now we took those patients and we gave them to look on a near field ophthalmic resolution chart. And what happens in this case, you see that because they have presbyopia, they don't have optical accommodation, they cannot change the focal length of their eyes, so they lose resolution. And you see that in the near measurement, we have a readout of 0.465 in visual acuity, which means that they have lost almost 5 lines in the ophthalmic resolution chart. Now we repeat the same experiment with the same people, but in this case we take the lenses and we add the extended depth of focus scratches on top of them. So we give them first the possibility to look on remote objects, and you see that they have 0.05 visual acuity, which means they lost some vision, but it is still more or less okay. Now, when we give them to read nearby object, they have 0.079, which is much, much better than what they had without the scratches, without the extended depth of focus. The problem with spectacles is that those scratches, they're on the surface of the lens, but when you look through those lenses of the spectacles, you can change your line of sight, and then the light will not pass through the lens as well, and this constructive and disruptive interference that we are seeking to have will not fulfill the design that we had. So we had a design that had many such scratches, and when we had many such scratches, the field of view through which the subject had this continuous extended depth of focus from near field to far field was almost over the full field of view. And you can see in the chart below, in the left lower part, that in 97% of the field of view, they had the correction of their vision due to those scratches that were distributed all over the surface of the spectacles. In the upper right chart, we measure not only what is the visual acuity, but also what is the contrast at which the people saw the different spatial frequencies. And we see that the contrast we measured with the extended depth of focus lenses is almost the same as you have with a monofocal lens when you have corrected vision, which means that the brain knows how to correct this loss of contrast, and the vision is good not only on the number of lines in the ophthalmic resolution chart that you see, but also in the quality of the vision. In the lower right part, we did the experiment on people with astigmatism, and again, we were able to fully correct astigmatic distortion, which were of 2 diopters, and without using cylindrical lenses, spectacles. Now we can speak about intraocular lenses. So we embedded the same concept for intraocular lenses, the lenses that they are being implanted in cataract surgery. And you can see the measurements that we did here in this slide, which were done in optical bench. You see how the extended depth of focus that we got, this is the dotted red line, is significantly larger. This is the z-axis. It's significantly larger than what you have in diffractive intraocular lenses, which is bifocal. It has 2 peaks, 2 focal lengths. So it can give you focus for near objects and for far objects, but not in between, not for objects which are in the intermediate distance. And you can see here some images. So this bifocal diffractive intraocular lens is called the Restore. And you see they give good image for far objects, good image for near objects, but very bad image for intermediate distance objects. But with the extended depth of focus, we have good image for far objects, for near objects, and also for intermediate distance objects. Everything is in focus continuously from near to far. Those are clinical trials that we have performed on subjects that the scratches were imprinted on the surface of the intraocular lenses that was implanted on them. And you can see a significant improvement. Let me briefly explain, for instance, this chart. We did here measurements on the right side, you see measurements of restore, and on the left side, on the right side, you have the measurement of the extended depth of focus left, and on the lens, and on the left side, you have the measurement of the bifocal lens, intraocular lens, the restore. Those are not normalized average visual acuity measurements. The different colors are different distances. This is 6 meters, 65 centimeters, 40 centimeters, and 25 centimeters. In this case, the lower is the better. And we see that with extended depth of focus, the near vision, the far vision, sorry, for 6 meters, as well as the vision at 65 centimeters and 45 centimeters, 40 centimeters, is much, much better than in the comparable case of experiment of clinical trials of the bifocal restore intraocular lens. Here you can see a subject that is wearing our contact lens with the scratches embedded on the surface of the lens. And we did clinical trials on contact lenses as well. Those are soft contact lenses. And again, as with spectacles, you can see that without applying the extended depth of focus, the distance vision is perfectly corrected. You have 0 visual acuity in logmar units, but you have 0.5 for near vision, which means they lost 5 lines, the subject, in the ophthalmic resolution chart. But when we apply extended depth of focus, you see that the distance vision is very good. It's 0 visual acuity, and the near field is also very good. It's only 0.1. And in mass scale clinical trials, we compare the performance of our contact lens with our extended depth of focus with a pure vision multifocal high edition contact lens fabricated. It's a commercial product fabricated by Bausch & Lomb. And you see that the performance we have is about 3 times better than the commercial contact lens. Now, the problem with contact lenses is that when you have those scratches, this is a schematic sketch of the scratch. This is from the side. The tears can enter into those scratches because they are large. And when they do, the optical functionality is destroyed. So how can we solve this? So we did add special nanometric structures on the surface of the contact lens. This is the surface of the contact lens. Inside the scratches, we added those nanometric structures, which have dimensions which are smaller than the optical wavelength. So for optics, they don't feel those structures, but because the structures are there and they are made from hydrophobic material, the tears, the water, the liquids do not enter inside, and the optical functionality is not damaged. This is how the contact lens looks like. Those are the scratches. This is what is seen inside the scratches. Those are the nanostructures. And indeed, those nanostructures function optically as before, while the tears do not go into those scratches. And optically, they function the same because, as I said, they are much smaller in their dimensions than the optical wavelength. We did the same also for RGP, for rigid contact lenses, and you can see the images that you get for near image and far image. This is monofocal lens, which is good for near, bad for far. A spheric lens, which is bad for both, and our lens, extended depth of focus, is good for near and good for far imaging objects, and for everything in between near and far. And what is, this is almost the last thing I'm going to speak with you in my presentation. Another thing which is very important in those extended depth of focus ophthalmic lenses is that they deal with a very problematic effect, which is called halo effect. Halo effect is when you have intraocular lenses, for instance, implanted with for people with cataract, then at night, when they look on bright light sources, they have like a ring, a halo around this source. And this disturbs them a lot for their night vision. So in our extended depth of focus, technology that in this case was embedded into RGP contact lenses, the halo effect is significantly lower in comparison to any other existing lens. You can see here, this is how the halo effect looks like for monofocal lens, so almost no halo effect. This is logarithmic scale, by the way. This is with our extended depth of focus lens. It's a bit worse than this, than the monofocal case, but almost the same. In the case of a spheric lens, you can see the very bright ring around the spot in the center, and this is very significant halo effect, and this is why regular aspheric RGP contact lenses are not good for night vision. Just to sum up and say that this extended depth of focus technology doesn't have to be used only for ophthalmic lenses. We also embedded it in microscopy and allowed microscope objective lenses that have both high resolution and very large extended depth of focus. You can see some experimental results here. For instance, here we image E. coli cells. This is with extended depth of focus where you see a lot of E. coli cells in focus. And here, this is in the case of regular objective lens that you see only 2 E. coli cells in focus and the rest are blurred. This is single molecular imaging and so on. This is in microscopy. And another application in which we embedded our extended depth of focus technology was for OCT, optical coherent tomography. This is the case with extended depth of focus. This is without extended depth of focus. This is with extended depth of focus. This is on the right side is without extended depth of focus. You see that the performance is significantly better. And here we did OCT on biological samples. And we saw that on the right side where we have extended depth of focus is the performance, the results of the OCT, optical coherent tomography, are much better than what we have in the left side, which is without extended depth of focus. So this was my presentation. I hope that you learned out of it and enjoyed an introduction into this new topic of how surface treatment could be used for ophthalmic applications. I hope it was useful for you.